With these, overall, we've eliminated a lot of separate components for control plane, for the image data store, for backup storage, network components, etc. And we've ended up with a physically much simpler cloud infrastructure without really losing any features or capabilities of these cloud systems. Right. Hi, everyone. I'm Boyan. I'm one of the founders of StorPool Storage. My talk today is this building high-performance, hyper-converged cloud infrastructure. And it's common quite often when we help our customers, we help them with not just the storage piece, but the complete cloud architecture and helping them optimize their whole cloud stack. So here's the kind of the main components of a cloud infrastructure as a service cloud. So there is a control plane. Right, so there is a control plane which consists of some management servers, database servers. There are compute hosts, which most people think, infrastructure as a service cloud is just a bunch of compute hosts. There is a primary storage system, and there are some additional storage services like image storage, backup storage. There are different network types like management network, VM network, etc. And one problem with this is that if you do it by the book, if you do it, you open how do I build a cloud, you start this thing with something like 20 individual physical components. That's just too complex for a lot of cases, and it's unnecessarily complex. Things can be done a lot simpler. So when the box our solution is usually put in is, we're just going to change the dual controller storage array. We're going to change that with a scale-out software-defined storage solution, and great things. Everyone's happy. But that's a very small step towards overall simplification of these cloud environments. There is a lot more that can be done. And this is necessary, moving to a software-defined architecture for storage. But it's insufficient. There is more than can be done for this. So what can we do? What we'll do is 20 physical components will go down to 7 physical components with everything. All the functions that we had before will be integrated into these fewer physical components. So first thing we'll do, we don't need a fiber channel network or dedicated storage network and some management network and VM network. All of these networks can run the same physical infrastructure. The second thing we'll do, so this is done with VLANs and on the switches. We'll converge storage and compute. So instead of having a standalone separate storage nodes and separate compute nodes, we'll run the storage system on the compute nodes. There are a bunch of, let's call them technical capabilities. So you can't do this with any software-defined storage system. You can do it with ours, for example. The fourth and fifth is that we'll virtualize the control plane and we'll abstract. We'll also virtualize these auxiliary services like image data store, backup storage, etc. So how do we do that? Well, instead of having external dedicated servers for the cloud control plane, things like CloudStack, OpenStack, we'll put them in a VM on one of the compute nodes. For a lot of kind of reasonably sized cloud environments, a single VM is enough to control, tens of hosts or even hundreds of hosts. And the image data store we will put again in a highly available virtual machine on one of the storage nodes. An interesting part of this is the kind of chicken and egg problem. since the compute nodes are managed by the cloud control plane, a high availability of the cloud control plane cannot be provided by the cloud control plane. So there is we, StorPool, provide in these environments a highly available virtual machine mechanism for the cloud control plane and for the image data store. And StorPool also provides the primary storage system with parallel I/O operations, data redundancy, data management, deep integration plugin with the cloud management system for snapshot-based backups in the same location and in a different location with the async replication to a remote site. So you largely, for all on-site backups, you largely eliminate the need for a separate storage for backups because in this concept, your on-site backups are just storage in your primary storage system. Your off-site backups then take additional space in a separate system. So this is what we started with: dedicated storage networks and separate networks for different things, dedicated storage boxes, special NVMe SSDs, and quite a lot of these cloud environments, with their complexity, they tend to have a lot of demand for working on them because they are more complex. And what we're proposing here is instead of a dedicated storage network, you have a normal Ethernet network and you use the same switches, the same ports on hosts, in most cases for both the storage traffic and virtual machine traffic, internet traffic, etc. Instead of having dedicated storage appliances or storage nodes, you do the scale-out software-defined storage for your VMs in a hyperconverged configuration, so you don't have the separate storage nodes. In terms of storage media, storage devices, you use just standard over-the-shelf NVMe drives. And instead of battling performance and availability issues all the time, you end up with, thanks to some capabilities of StorPool, you end up with a very large performance headroom and a highly available cloud solution. In terms of resource utilization, this is kind of graphically roughly what it looks like. The blue part, vast majority of the compute and memory resources of these compute hosts you can run your virtual machines on. StorPool only takes like 10% of the compute and memory resources of these hosts, depending on how large they are. In typical configurations, it would be between 85 and 90% of the compute resources are available for user VMs or your own VMs. In terms of redundancy or redundancy schemes, the control plane, the way we've done a bunch of these cloud deployments is the control plane uses an active-passive redundancy scheme, which means that because it's simpler and because it's good enough, like the failover times of the scheme are within a few minutes. So if anything happens to the host that runs your primary control plane, it only takes a few minutes for the cloud environment to become available again. In these few minutes, they obviously are a control plane downtime, but they're not workload downtime. So virtual machines continue running even if your control plane is not available for a few minutes. For memory, there is no redundancy for memory. There is some spare capacity. So one way to calculate it is that in one physical node, the capacity of a single physical node would be left for memory, for RAM spare capacity. In a 10-node cluster, this is just 10% of RAM reserved for these purposes. CPU redundancy of CPU is done through increasing CPU oversubscription. So you might have a lower CPU oversubscription factor regularly and a slightly higher one when a node has failed. Storage redundancy we do with either three-way, 3 copies, or with N+2 erasure coding with our system. And network redundancy is 2N. So you have two completely independent switches. Whatever happens to one of the switches, you still have another one available. So in summary, control plane runs on HCI hosts with a simple HA scheme, which is provided by our solution. Image data store, which is the place where you keep your VM templates and your ISO images and things like that, also runs as a highly available VM inside managed by StorPool. And even though there is an image data store, it's just the way these cloud management systems like CloudStack, OpenStack, Proxmox, etc. work is they insist on having a separate file share for images. Even though there is a separate file share for images, our deeper integration with cloud management systems enables us to do instant provisioning of virtual machines via instantaneous clones of these images. Backup options, so on-site backups you could do with snapshots in the same cluster, or you could have a separate backup cluster, or in addition to that, you could have an off-site backup by creating regular snapshots and sending them to the remote location. And this could be something like snapshots every 15 minutes, 30 minutes, 1 hour, or daily if you don't really need the per hour snapshots. With these, so overall, we've eliminated a lot of separate components for control plane, for the image data store, for backup storage, network components, etc. And we've ended up with a physically much simpler cloud infrastructure without really losing any features or capabilities of these cloud systems, cloud services. In this concept, in the HCI cloud infrastructure concept, the way we build large cloud environments is by having multiple clusters. Let's call it the building block concept. So you have a rack of servers, and within that rack of identical servers, you have a cloud environment which is, in terms of availability, completely independent from the availability of your other clusters in the same data center. And what you do on top of that is you do some, call it management unification. So the users of the cloud don't need to know that there are multiple building blocks within the cloud. You connect these over a higher level a network. This gives you simplicity and maximum availability in each cluster. There is no dependency between the clusters, so whatever happens in one of them doesn't affect the availability of the others. And you still have live workload migration between these clusters. So for the purposes of, for example, balancing your usage between your resources. Typically, these would be clusters with, say, 15 hyperconverged nodes and larger deployments would be multiple clusters. So the scalability concept is also fairly simple, right? Another thing we'd like to mention is the StorPool storage systems deployed in this way, in this hyperconverged concept, are fully featured storage systems, StorPool storage systems. So you could have a hyperconverged cloud environment and then also use the same storage system to support additional workloads outside of the hyperconverged cloud environment, be that bare metal servers, VMware clusters, etc. You keep the flexibility of, a major objection to hyperconverged is that you must deploy compute when you deploy additional storage. With our solution, you keep the flexibility of adding just storage capacity, storage performance, by adding storage nodes to these. And this hyperconverged concept is supported with all of the integrated existing cloud management platforms that we support in the KVM ecosystem. So that would be CloudStack, OpenNebula, OpenStack, Proxmox, Oracle Virtualization, Overt, KubeVirt, and etc. Right? So we have plugins for basically everything, everything popular. And I also have an example configuration to give you ideas about the levels of density and efficiency that can be achieved with these setups. So the example is a 5-node cluster that has these kinds of parameters, and it's able to run 1,500 basically virtual machines with 4 GB of RAM each. Obviously, it's not the only calculation you can do. You can have all, you can change the memory to 8 GB, and then you would get half the number of VMs in this example. The next one is I have performance numbers from not from benchmarks, but from a real production workload of one of the clusters used by one of our customers, which is built using this hyper-converged cloud concept. It's similar size to what we discussed before, so it's around this level of resources, so let's say about 6 terabytes of memory and about 960 not oversubscribed vCPUs, right? So that one has, on average, 120,000 IOPS, reads plus writes load over the course of 1 week. So you can see that even though there are thousands of virtual machines, the actual storage average storage load is fairly low. And the peak storage load in this particular cluster is about 400,000 IOPS, read plus write. It's a relatively small, say, 10-node cluster, 5-node cluster. And I have to point out that these numbers are the production load. They're not the performance capacity of the system. The performance capacity of the system might be 5 times or 10 times the actual load percentage. So one thing that kind of is important to understand with StorPool storage systems is that quite often the performance capacity, the performance headroom of these systems is significant. So you don't, even though you take it into account when planning a deployment, it's very rarely an issue. Another thing with this, so this is the per second average latency of storage operations in this cluster, which is for a mix of different operation sizes. So there are some operations which are, say, 120 kilobytes, and there are other, say, 4 kilobyte operations. The which makes the average latency a bit useless, but here are the averages. So with the production load, this cluster is able to do less than, say, 660 microseconds for writes and 300 milliseconds for reads. Yes. Here's some of our customers. Some of them, a couple of the logos on the screen represent customers that use this architecture, the hyperconverged cloud architecture with us. So Catapult, Namecheap, Cloud Sigma, Dustin. And we're at booth G20. Talk to us about building either storage for your infrastructure as a service cloud or design of a whole cloud environment with a hyperconverged concept or otherwise. Yeah, thank you.